Okay, so let's recall that in the exercises that we have been solving recently, we actually calculated quite a few limits, and we also figured out when a limit does not exist. But in almost all of them, the methods that we devised were somewhat ad hoc. We did not really know beforehand what to do. Once we had a limit, we then and there itself we somehow figured out whether it exists or not, and if it exists, what to do, how to calculate the actual value of the limit. But now we want to do those things systematically, and we want to learn the general rules that are behind these methods. So in this next section, we are going to look at rules for finding limits. So the first set of rules are going to be about limits of powers and algebraic combinations of functions. And the first theorem just involves that. So the things you are going to see here are collectively called properties of limits. And they are very straightforward and easy to remember. You will see now. So let's see what the things are. So say you have two functions f and g, and say their limits as the independent variable x approaches c are given to be L and M respectively. So you can understand that c is a real number such that in an open interval containing c, both f and g are defined except possibly at c, because that's what the informal definition of limit requires. So we have those things, and these two limits are given. And also, just to clarify things, L and M are real numbers. They are not infinity or anything like that. So the first rule is the sum rule. It states that the limit of the sum of f and g is just the sum of their limits, that is L plus L. Just like that, the difference rule says that the limit of the difference of them is the difference of their limits. Similarly, you have the product rule. You take the product of the functions, then you calculate its limit. It turns out to be the product of the limits. So it is that straightforward. There are other parts also. Let's see what they are. There are similar formulas, if you want to call them, to calculate derivatives, which primarily are rates of change, instantaneous rates of change. Those formulas, however, once we have them, we will see that they are not as straightforward as these ones, but these are absolutely straightforward. So the fourth one is the constant multiple rule. It states that the limit of k times f of x as x approaches c is k times the limit of fx, that is L, where k is some constant. That means k is some real number, which constant in the sense that k does not change with x. You can change x, but k will remain k. Then there is this fifth one, which is the quotient rule. Yes. It states that the limit of the quotient of f of x and g of x as x approaches c is going to be the quotient of the limits L over M. And in order to for this to be meaningful, you have to assume that m is not equal to 0, because otherwise the right hand side becomes meaningless. Actually, some other assumptions also should be mentioned here. If one really wants to be rigorous, some assumption about the functional values g of x themselves. However, the authors are not going into those subtleties, those complexities right now itself. That is because the kind of f and g that we are going to consider, we are going to actually see in the problems, in the examples, the kind of functions f and g that we are going to encounter there, they automatically satisfy those conditions that I am talking about, which I am not mentioning here, and the authors also haven't mentioned. So, in order to not make things needlessly complicated, we just assume that here m is non-zero. You may guess what the problem is here with the left hand side. You need not just m to be non-zero, but you also need the g values to be non-zero, at least somewhere around c. So that extra condition should actually be assumed. However, what I am saying here is that the kind of f and g that we are going to consider automatically satisfies that condition, and that fact comes as a consequence of this itself. All these things have something to do with the notion of continuity. We haven't got that yet. Okay, so let's just assume that this is all we need in order to apply the quotient rule. That is, what you just simply need is m to be non-zero. That's it. Okay, for now let's not make matters more complicated than this. And there is one more, the power rule, which involves powers of functions where the exponent is a rational number. So this is the sixth one. Power rule. If n and m are integers, then the limit as x tends to c of this power of f where the exponent is n over m is equal to this power of the limit, provided this is a real number. Now, why do we need this provision? Can this be, can we have a case in which this is not a real number if we are not careful? Yes. For example, your original L can be negative. Say the original L is -1, and say you have n equal to 1 and m equal to 2. Then L to the power n over m is not a real number, it's a non-real complex number. The imaginary unit square root of -1. So we do not need that. So that's why this is applicable only when this is a real number. Okay, so these are the rules. Now, among these rules, in the next section we are going to see the proof of the sum rule, that is the first one, that is the limit of f of x plus g of x is L plus L. We are going to prove that in the next section, and the remaining rules except the last one are proved in the second appendix, appendix 2 at the end of the text. And this one, the sixth one, is proved in a more advanced text. More advanced text means it's not available here in our text. Okay, so we just leave these things like this. Now, the proofs of these things are not what we are aiming at. Our main aim is to be able to apply these things to calculate actual limits. Okay, so let's see the first example, where we are going to apply these rules to calculate this limit. So it is presented as a question itself. Find the limit of this rational function. A rational function is a quotient of two polynomial functions. Such functions are called rational functions, where the numerator polynomial is this cubic polynomial x cubed plus 4x squared minus 3, and the denominator polynomial is the quadratic one x squared plus 5, as x tends to c, where c is any real number. Okay, c can be any real number. So you can understand that the way we calculated the limits in the previous exercise set will not work here, because you don't know what c is. C can be any real number. So you are not in a position to, well, if you want, you can draw the graph of this function, but then based on different values of c, you will have to see quite a few examples to decide what the limit is, and that process itself is exhausting. It is time consuming. Instead, if we apply these rules, then we can calculate the limit quite easily. Let's see how. Solution. Note that by the sum rule okay, if I write like this, I will have to write a lot. Note that by rules 1, 2, 3 and 4, limit of the numerator, let us calculate that separately. But we are going to write many steps so that we can see how exactly we are applying the rules. So first of all, what happens is that we apply the sum rule and the difference rule, because here you can see that we are looking at a sum and a difference of three functions. One of them is x cubed, another one is 4x squared, and another one is the constant function 3. So by the sum rule and difference rule, this limit will be equal to this limit minus, well, let me be absolutely rigorous about the application of these rules. Let me consider this as minus 3, because then you can interpret this as not a difference actually, but as a sum of three functions. So we have applied the sum rule 2 times actually. you can think of it that way also. So first of all, you apply the limit to this function, then plus to this function, and then to this sum you once more apply the sum rule, getting this. Oh, I have already written 4 outside now. So it's just this. But the keen-eyed viewer may already have a doubt. Some of you may be thinking that what I have done here is really not quite correct, because according to theorem 1, first of all I have to make sure that these limits exist, because for example, if you forget about minus 3 for a moment and say you have only these two functions, then this is the f of x and this is g of x. The fact that I have applied the sum rule here requires me to first of all know that these limits exist. Unless I know that L and M exist, because that is given in the theorem, I should not be able to apply the sum rule. So strictly speaking, simply writing this is not correct, but we are eventually going to see that ultimately what the limits that we are going to encounter, they will exist. Okay. So with that in mind, I am just simply in a way blindly using these formulas without knowing whether what I am going to get at, those limits will exist or not. But I somehow know, say I know that those limits exist, and I already know that they are given, so I am able to apply the formulas. So let's now move forward. Okay. Now what do I do with this? Here I am going to apply the power rule with n equal to 3 and m equal to 1. If I do that, then I will get this. Plus, now you may already know what we are trying to do here, so I can skip steps and apply the constant multiple rule and the power rule simultaneously. The constant multiple rule allows me to take 4 outside, and then the power rule allows me to take the limit inside x square, thus giving me this. And this last limit is minus 3 itself, because we know this, since it's a constant function. No matter what happens to x, all the values are going to be constantly minus 3, so I'm going to get minus 3. So now we come to the question of do we really know that this limit exists? Because otherwise I should not have been able to apply these formulas, but I know that this limit exists. And in fact, this limit inside the Q is nothing but C. So that's how I get CQ. Plus here I get 4c square minus 3. Okay. So I know the limit of the numerator. Now similarly, I will also know the limit of the denominator. So in fact I am going to write similarly means similarly applying the rules that are required to be applied in this case. Limit of x square plus 5 is going to be c square plus 5. And note carefully that this is not equal to 0. Regardless of what c is, this is never going to be 0 due to the structure of this expression. So we know that if you are thinking of this as L and this as M, then M is non-zero. So now we can apply the quotient rule. Hence, by the quotient rule, we have this equal to, let me write here itself, L divided by M. L is this and M is that. That means C cube plus 4C square minus 3 divided by C square plus 5. So this is the limit. And in fact, now you can see that this matches with what we were doing back then, where we were solving those exercises. Now we know why the things that we did there are actually justified. They are justified by theorem 1. Let's now see another one. Find limit of, this one involves radical 4x square minus 3, but we need not worry because this case is also covered among the parts in theorem 1. Minus 2. So you can understand which of the parts we have to use here. I mean, primarily, what should we do first of all? What to do about the radical? The radical is actually nothing but a power, right? So it is nothing but 4x square minus 3 to the power 1 over 2. So it is again in that form, f of x to the power n over n. So that's it. By the various relevant parts of theorem 1, we have so what will it be? 4 times 4, 16. 16 minus 3 is 13. So square root of 13. So this L to the power n over m in this case is square root of 13, which is a real number. And that's why we have been able to apply the rule 6 in the first place. Okay, so this is the answer. There are many things that one can ask. For example, because in calculating this limit, we are actually not looking at what is happening at x equal to minus 2. No, that is not the concern, but what is happening around minus 2. What happens when x is very close to minus 2? Now the question that naturally arises is this. For such values, is this going to remain a real number? But right now, we are assuming that such questions will not cause any problem, and that whatever we are given in theorem 1 can simply just be applied and we can find the limits. We did not worry about such questions. Such questions we will answer in a much more advanced course. Okay. Now, in the course of calculating this limit, you have seen that you calculate limits of polynomial functions. For example, this polynomial function, and applying the sum rule, power rule, product rule, in fact all of them. In calculating such a limit, you ultimately end up realizing that all you have to do is replace x with c, with the point where the independent variable is approaching. That's it, that's all you have to do. So that gives rise to this theorem. This is theorem 2. Limits of polynomials can be, so we have this heading sort of thing. Can be found by substitution. Is it that? Yeah, just substitution. That's actually the whole thing. And specifically it means this: if say p of x is this polynomial function a n x to the power n plus a n minus 1 x to the power n minus 1, and it goes on like that till we reach the constant term a naught, a0, then the limit of p of x as x approaches c, where c is any real number, is nothing but p of c itself, which if you use the expression it becomes this. And this fact that the limit can be calculated just by putting the value, putting x equal to c, is the notion of continuity. Although we haven't got the notion, or it's not still the time to get the notion, but I keep on repeating this so that by the time we reach continuity, we will have become accustomed with it really. Okay. By that time we will be well accustomed with the notion of continuity. Okay. And you have also seen in that example that not just polynomials but limits of rational functions can also be calculated just by substituting x equal to c, and that is the next theorem. Note one thing carefully, that we are just simply going on stating the results as theorems or lemmas or whatever they are. But proving these things, although the things themselves are quite straightforward, but proving these things, all of them are not exactly that straightforward. Okay, but we'll leave the proof, of course. Limits of rational functions, just like polynomials, can also be calculated by substitution, with one condition, of course, because you need to make sure that the denominator is not 0 after you make the substitution. Can be found by substitution, provided the denominator is non-zero. And the mathematically that thing is just this: if p of x and q of x are polynomial functions, then the limit of this rational function as x approaches c is just p of c divided by q of c, provided q of c is non-zero. Okay, so instead of mentioning all those things while calculating such limits, like this one or this one, instead of mentioning all the things, all the rules that are coming from theorem 1, how they are being applied, you can just simply apply these two theorems and get the job done in maybe 1 or 2 steps. And now we are going to see how that can be done with some more examples. This next one, example 3. Here we have to calculate, means it's given, it's not given as a question but just as a fact that this limit of what is the function x cube plus 4x square minus 3 divided by x square plus 5. Is it that same thing that we had there? Yes, the same function actually. But there we had x approaching c. Here a specific value is given, minus 1. So by applying theorem 4, it is just, I don't have space to write here, minus 1 cube plus 4 times minus 1 square minus 3 divided by minus 1 square plus 5. So this is what will the numerator be? This will be minus 1 plus 4 minus 3, that means 0. So we are going to get 0, and the denominator of course is non-zero. There also we saw that regardless of what the value of c is, the denominator is non-zero. So here also non-zero, in particular for c equal to minus 1. Okay, so you can see how quickly you can calculate the limit as opposed to actually looking at the graph of this. You can appreciate how much these theorems help in calculating such a limit. Without the theorems, what would you have done? You would have had to look at the graph, which you can do in a graphing calculator. And then you have to see what is happening near x equal to minus 1. From that you would have to guess the limit, and then you would have to maybe by constructing some table of values of x near minus 1 and seeing what is happening to the functional values, you would have to match your prediction about the limit that you get from the graph and your prediction of the limit that you get from the functional values. From that you can guess, okay, this is the limit. But now just a simple application of the theorems immediately gives you the actual value of the limit. Okay. Next we see another example where also we will encounter such a situation, but here you may not be able to just simply substitute because of a problem, and it has been given a name also, cancelling a common factor. Actually these are the tricks that we have already seen while we were solving those exercises, but now we are looking at these things, same things, more systematically. So here the problem is to evaluate this limit. Okay, so the form of this limit is just like what you have in theorem 4, but unfortunately you won't be able to apply theorem 4 immediately because q of c is equal to 0 here. Here q of x is x square minus x, c is 1. If you substitute x equal to 1, you get 0. So that means you cannot apply theorem 4. So what to do? Note that x square plus x minus 2 divided by x square minus x. So this is, if one tries to factorize this numerator, then it can be done in this way. Let me check. X square plus 2x minus x is plus x minus 2, yes. And the denominator of course also can be factorized like this. And now comes the crucial realization that in calculating this limit, we are x is varying over a region near 1 but never becoming equal to 1. Okay, always remember this. When you look at such a limit, x is not equal to 1. X is not equal to 1, no, never. You can take x equal to 1, but that has nothing to do with the value of this limit. It may happen that if you substitute x equal to 1, you get a value that is equal to the value of the limit. But x equal to 1 does not contribute anything to the limit. You have to understand this. The values of x near 1 determine what the limit is, if it exists. But the value 1 itself has nothing to do with the limit, at least in finding out the limiting value. X equal to 1 plays no role. So that is why x minus 1 is not equal to 0, and that is why we can cancel x minus 1 to have this more simple quotient for all x not equal to 1. And because in our limit x is not 1, so now we can use this instead of this. So note that in this step we haven't used any theorem, but now we can apply theorem 4. because if we substitute x equal to 1, there is no problem. So now by theorem 4, the limit is just this, that means 3. So because of this trick, this type of problems are named cancelling a common factor. Okay, but things can get even a little more complicated than this also in a similar situation. It may not be obvious that you have a factor that is common that can be cancelled, but you may have to produce such a factor. So the next example is about that. Creating and cancelling a common factor. Okay, and the limit you have to find is this. Find the limit as h approaches 0 of square root of 2 plus h minus square root of 2 divided by h. Okay, so you can see here that although the form is that of p of x divided by q of x, there are two things here. The first thing is that although the denominator is actually a polynomial in h, the numerator is not, because you have radical. And the second thing is that it's not so obvious what can be cancelled. You can see that there is a problem in putting h equal to 0. So the denominator h somehow has to be removed, but how? We have actually you almost I am almost sure that you know how. So what we have done here, we have multiplied and divided by this same expression. But just like you should be very careful before cancelling common factors, making sure that it's non-zero, you also have to be careful about doing that similar thing here also. You should be sure that whatever you are multiplying and dividing the expression by is non-zero. Can this be 0? No, it cannot be, because the moment you use this now, it means that this is always greater than or equal to 0, and this will be, inside whatever else you have, this real number is always greater than or equal to 0 and will be equal to 0 only when c is equal to 0. Otherwise it is positive. Okay, now you may of course say, okay, for h equal to minus 2 it does become 0. Fine, but can this sum be 0? In order for the sum to be 0, this radical, this value should be equal to minus square root of 2, but this is never minus, this is always non-negative, it is never negative. So that's why this is always non-zero. So this step is a legitimate step. no problem with this. And now if you use your usual a square minus b square formula, you then get square root, square of that, not writing those things, and you have to mention for all h not equal to 0, and which is something we need in the beginning itself, because otherwise this is undefined, and in our limit h is non-zero. So now we have successfully removed h, although at first glance it was not obvious how to do that, but by creating extra things we have managed to bring h, managed to create h in the numerator and then cancel it with the 1 in the denominator. So limit of the function as h approaches 0 turns out to be equal to this, and this is equal to root 2 plus root 2, that is 2 root 2. Note carefully, we are not applying theorem 4 here, because theorem 4 requires a rational function, a quotient of two polynomials. Here the denominator is not a polynomial, but still we are using the quotient rule. Okay, so that's why we are able to take h equal to 0, and that is going to be the whatever value we are going to get by doing that, that will be the limit. So this is the limit. Next we have a very important theorem. It has a name. The name itself helps us remember what the thing is. The sandwich theorem. It's a very intuitive one. It's very easy to understand why it should be true, and that's why it's easy to remember it also. And its theorem, I have written this theorem 4. Oh, so that, okay. Limits of rational function, that was theorem 3. I was continuously calling that theorem 4. So now only we are going to get theorem 4. Anyway, so it involves three functions. One of them is sandwiched between the other two. In what sense? Let's see. Suppose that g of x is less than or equal to f of x, which is less than or equal to h of x, for all x in an open interval containing some real number c, except possibly at c itself. So that means we have all the things in order for us to talk about the limits of these functions as x tends to c. Suppose also that limit of g of x as x tends to c is, it exists, it is some value L, and that is also equal to the limit of h of x as x tends to c. So here f is sandwiched in between g and h in this way, that the f values lie in between the corresponding g values and h values. And also the outer functions, if I call these functions outer functions, they both approach a common limit L as x approaches c. Then the statement is, the claim is that the sandwiched function also approaches L, that same limit. So if you think of this thing in terms of, it's very easy to believe why that should be the case. In terms of graphs, if you want to understand what is going on, then it's roughly like this. So this is your C. Although we are showing C to be a positive real number, but you should understand that C can be negative also. Also it can be 0. It is just anything. And say this is an open interval in which all the three functions are defined except possibly at C. At C maybe they are not defined. And suppose, because we have said that the functions are defined in this open interval, so we need not look outside the open interval. So the graph will lie in this strip itself. Say the graph of g of x, oh, I have to be careful about which one lies above which one. Actually, these graphs will not touch these lines. So this is the graph of h of x, and this one is the graph of g of x, and the graph of f of x is like this. And on that side also, this is the graph of g, this is the graph of h, and this is f. So you can see that for any x in the domain, this point is h of x, this is f of x, and this one is g of x. So g of x is less than or equal to f of x, which is less than or equal to h of x. So that's why the graphs look like this. Now you understand that if it happens that these two limits are L, so this value is L, then the graphs are going to come very near L as x is nearing C. So because the function f is sandwiched between these two things, no matter how it behaves in the other part of the domain, the moment it also comes near C, it is bound to come near L. It has no other choice because these two things will push it towards L. Okay. So using this fact, we can actually prove calculate many limits. So the author has given two examples. And we will see other such problems where sandwich theorem has to be used in the exercises. So let's next see example 6. Given that 1 minus x square over 4 is less than or equal to u of x, where u of x is some function which is less than or equal to 1 plus x square over 4 for all real numbers except at x equal to 0, possibly find the limit of the sandwiched function as x approaches 0. Keep in mind that the sandwich theorem is only applicable if the outer functions approach the same limit. If the outer functions approach different limits, then f is not so restricted. So in that case, we don't know whether the limit of f is something that we already know, or even if it exists, we cannot say that. So the only thing we have to show here is that these two functions approach the same limit, then that value will be the value of this limit. Since, but that is just simply absolutely straightforward. Using the properties of limits from theorem 1, we can almost immediately see that this limit is 1, and so is this other limit. So by the let me just write ST, by the sandwich theorem, this is also equal to 0. And you can see how general this result is. It does not matter what the actual function u of x is. If these inequalities are true, then all such functions are bound to have limit 0 as x approaches 0. But now we are going to see another example in which the functions are concrete, nothing general like this. Example 7. In this example, show that, well, we do have a general function, but it's not about that function itself. If limit of absolute value of f of x as x8 is it 0? It's just anything, c, any real number. Then this is also 0. Yeah. We know that we already know these inequalities from properties of real numbers and absolute values. For all x in the domain of f, here itself let me include the condition, because in calculating these limits, this one and this one, x equal to c is not a case, so that's why we are considering this. Since we have these things and the outer functions in this case both approach 0 as x approaches c because of what is given. So by sandwich theorem, this is also equal to 0. It's not now just a matter of writing. And the sandwich theorem implies that the limit of the original function without the absolute value is also 0. And with this, the current section ends. After this, the exercises are there to solve. That we will start in the next calculus update. So I am ending the video here itself. Our next upload is this coming Friday, of course, and on Friday let's again go back to field theory. We have been dealing with that section where we are using field theory in deciding this notion from geometry about this notion of constructibility of geometric objects. So there we have already seen many things, but we are yet to see the main theorem, the main result that will lead us to something using which we will be able to decide whether a geometric figure is constructible or not. So that we will see this coming Friday. So with that, this is the end of today's video. So see you on Friday with our main theorem on constructibility. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.